We are back once again. This is day 45 of the daily LeetCode grind. We're back once again. Reflections on yesterday. So yeah, we were doing a lot of prep, basically like 5 to 6 hours after work. That was too much prep, and even last night I usually do an hour and a half on recording, but off stream is like 5 to 6 hours after work. But yeah, I couldn't even do the 30 minutes. I was doing this problem and I literally just couldn't think straight. So too much back-to-back problems. It needs to be like good breaking, like good like breaking up the session to make it make sense. That being said, I think we can solve this problem, but graphs aren't our strongest suit. So this is also basically another chance to find a way to actually make this make sense. We had like 2 submissions yesterday that we're just trying to put together, and we weren't really thinking through, weren't really taking a chance time to figure it out. So we have this explore card here, and we have these 2 problems which seem pretty difficult, but couldn't really figure out how to find the right angle on them. But I think the goal would be to be able to do the top 3 problems in each category, and then we'll go back to the top and just get blocked, right? Hopefully we have a better understanding of graphs in general, we can push through, but apparently this is solvable with union find. Both of these, right, we couldn't figure it out. And additionally, depth is also, these problems are also solvable with depth first search, so we need to be able to figure these out. But we should be able to figure out if path exists in graph. But yeah, I think that's just the relationship between like doing new problems and focusing on older problems. So I think what I've heard, at least some people say that helps them the most, and I think is like pretty much using struggle as an elaborative encoder. So if you can't do the problem, just keep trying anyway, and then you dump like 10 hours into it, then you look at the solution, and I feel like you just never really forget the solution, because you pretty much explored all your paths, and now you see how the solution is broken up. That being said, we're going to try this for this one, and then afterwards we're going to try all paths from source to target, which is a medium, and then I think that should make sense. I'm also realizing that topic-based studying is just much better than random problems. So topic-based studying with supplemental reading might actually be the state of the art. And so that might be the play. We also had 2 people join, or one of the 2 people joined Discord. So shout out to I'm That Guy. He left a W comment. He also had a W entrance into the Discord. Good comments and good ideas exchanged. That being said, the grind does not stop, and you know, we have like 2,000 more LeetCode problems to do, so we have to get to work. Our TC is currently peanuts, so we got to fix that. And so we're going to jump into with find if path exists in graph. And don't forget to join the Hyperbolic Coding Chamber Discord. Also, leave a comment if you think we should change this to streams, maybe daily stream, like 7 p.m. or 8 p.m. So we're already 45 days deep, so maybe doing it with other people could help, but also maybe doing it on stream might be more distracting, but I think the community aspect might be pretty cool. So that would be the goal. And so, yeah, so we're going to jump into find if path exists in graph with 1 hour and 30 minutes on the clock. And we're just going to remove the previous solution we had, but we'll inspect it for a bit to start and then jump into it. So yes, don't forget to join the Hyperbolic Coding Chamber Discord. Also, if you're doing something similar, if you're doing your LeetCode problems, drop your LeetCode profile, give me some tips, give me some insults, and we're just going to jump into it. So we have find if path exists in graph. There's a bidirectional graph with n vertices, where each vertex is labeled from 0 to n-1 inclusive. The edges in the graph are represented as a 2D integer array edges, which makes sense, where each edge sub I is equal to u sub I. V sub I denotes a bidirectional edge between vertex u sub I and vertex v sub I. Every vertex pair is connected by at most one edge, and no vertex has an edge to itself. Let's understand that every vertex pair is connected by at most one edge, but it can be more, and no vertex has an edge to itself, so there's no self cycles. You want to determine if there is a valid path that exists from vertex source to vertex destination, given edges and the integers n, source and destination, return true if there is a valid path from source to destination, or false otherwise. So we have, let's map this problem statement to the example. We have n equals 3, so we have 3 vertices from 0, 1, 2, because they said n minus 1. We have an array of edges, which denote an edge between 2 vertices, and then we have a source, which is source 0. We want to know if there's a path to vertex 2. There are 2 paths, right? And I think they're kind of giving us the answer here, but there are 2 paths, and yeah, there are 2 paths, so we can return true, right? In this graph, we can see that the edges that we're given 5 total vertices here, but even though we have edges, there's actually not a connection between both these graphs, so there's actually no way to get from 1 to or 0 to 5. And so that is important. So I think what we could do, let's see what we tried to do. So it looks like we had a depth first search. We converted the edges to an adjacency list, which I think did make sense. And then we wanted to traverse the adjacency list and search for destination, right? Turn DFS, visited source destination, right? And so we had a couple of parameters. We had adjacency list, right? Visited set, cur, and destination. We said if cur equals destination, we want to return true. Now, if visited doesn't have cur, then we want to add it, so we don't want to revisit it. But we want to visit all the neighbors of 0. So we did const n of neighbors. So we have 1 and 2, right? If we haven't visited n, so we'd have 1, right? But if we haven't visited, and also if the adjacency list has n, then we want to remove a simple cycle. So let's look what we try to do here. Now, if then we do a DFS. We do a DFS on n. So we go to 1. 1 has no longer has an edge to 0. We've already seen 1 before, so we don't do anything. Then we'd go to 2, remove the simple cycle. We haven't seen it before. And so I wonder what the problem was with this code. It looks like it ran. And so it looks like it did run. Oh, it looks like we ran out of time. So it looks like, right, for a sufficiently large test case, it looks like we completely ran out of space. And that makes sense. I mean, we have a this would be a really deep recursive stack. So that would actually be a lot. So if we're doing valid path, we actually can make this bigger. We have a depth first search, and we can do this with depth first search because that's what this problem is tagged with. You have to find a valid path, and so that's interesting. That is interesting. I wonder if there would be a way interesting source. So I mean, I'm seeing there's one way we could use union find, right? If we know that our source is not a part. Wait, that could be interesting actually. Wait, we could use union find for this now that I'm thinking about it. We have a source and a destination, right? We just have to check if the source's root node and the destination's root node are the same. And if they're the same, the source and the destination root node are the same, then the path exists between them because they're part of the same set. But if they don't, right, then we could just return false. So now I'm thinking this whole thing could be solved with union find. So let's just make sure that makes sense. We would have an edge between all these nodes, and we could check if the root node of source and destination were the same, then we would know an average constant time whether or not they were the same. So the goal would be create UF data structure, right? We'd have we want to load edges into UF, and then return if UF.find source equals UF.find destination. And that would mean that there actually does exist some path. So let's go ahead and do that, right? And so we're going to implement the union find with the root and with the union by rank optimization, as well as path compression for the find. And to do that, we're going to need a root array, which is basically going to store a map of the literal index element to the actual value, which is going to be the root node. We're also going to need a rank array. We're going to have a constructor, which is going to take the number of vertices, which is going to be a number. And when we do get that number of vertices, we're going to use it to initialize our root array. So we'll say let I equal 0. I is less than number of vertices, and do I plus plus. And like they said, the vertices are going to be named from 0 to n minus 1. So this works pretty good for our root array. And a root array, when we start, we want every node to be isolated. So the literal index is going to share the same value as its, the literal index in the array is going to share the same value as the actual index. So what I mean by that, if we have an array at index 0, we're actually going to have the value 1. At index 1, we're actually going to have value 1, and so on. And so we're going to do this dot root dot push 1, and then instead of the rank array, we're going to push 1. Then we're going to need the find function, right? We're going to take a component x, right? And we're going to want to return the root component for it. And so we'll let a temp value equal x. And the way you know when you found a root is when the literal component name is the same as the value in the array, which would mean that the index, the vertice is its own parent node, which means it has no parent, which would mean it's a root node. Say while temp does not equal this dot root sub temp, right? We're going to want to say temp equals this dot root sub temp, right? And so if we have an array like this, right, and we have index 1 and index 0, if we do this dot find on 1, we're going to say, hey, is 1 equal to this dot root sub index 1, which is 0? No. So we're going to say temp equals this dot root sub temp, which is 0. Then we're going to say, hey, does 0 equal this dot root sub index 0? And it would be now, because we're going up through the graph basically, so we can return temp. And then for union, right, we'll take a component x and a component y, and we won't return anything. And we're going to unite them if their roots aren't the same. So we have to get the root for x. Do this dot find of x. We can duplicate this for y. So this dot find y, and we'll say if root dot x is not equal root dot y, right? Then we're going to want to combine them based on the ranks, right? So if this dot rank sub root x is greater, right? If its tree is larger than this dot rank sub root y, then what we're going to want to do is say we're going to pretty much attach root y to root x's tree. So we're going to say is this dot root sub root y, its new root is now going to be root x, right? Else if this dot rank sub root y, if root y's rank is greater than root x, then we're going to say then root x is root node, right? It's now going to be root y, because we're going to unite root x and root y, but it's going to be root x, which is joining root y's tree. Now, if they're both the same rank, we're just going to attach root y to root x's tree, and then we're going to increment the rank of root x. Now, this does make sense so far, so I think what we'd have to do to solve this, we'd say UF equal our new quick union equals new quick union, and we take in n, and we actually call our class union find. So we'll call this UF, and we'll call this union find. This is actually really low to the bottom of the screen. Make this a little bit bigger. Now we want to load the edges into union find, so we'd say for const right, vertice 1 of the edge, right, and vertice 2 of edges. Right, we're going to say UF dot union v1 and v2, and then we can return UF dot find source equals UF dot find destination, and let's see if this makes sense. So it does work for the first case. Nice. Now that is actually pretty dope. 409 milliseconds, 93%, 85%. That's a feels, yeah. So that's why earlier we said like blocking on a problem. Been stuck on this one. But I knew this one we solved in like 13 minutes. Saw it through. Yesterday on too much practice and low sleep, I just couldn't see what was going on. But yeah, that was a feel strong. There's actually no solution for this question. I wonder if anyone else used union find. Looks like our window is frozen. Had to reset Chrome. So yeah, that's actually pretty cool. There's no solution for this yet, which is interesting, but it works really well with the union find. So yeah, I'm not certain how I didn't see that before. We don't actually need to keep track of the path, so that is pretty cool. So I'll paste this into the Explore card. We'll have find if path exists. Wait a second. Oh no, I think this just loaded my solution. Yeah, I just loaded my solution from the. That's pretty cool that they have hot reloading like that. So that works. So the way they solve this was actually different. They have an adjacent, so they have valid path. They create an adjacency list, right? For underscore in range n. They create A and B and edges. So they do create an adjacency list like we did. And they connect an edge between both. They create a stack, right, which is going to have the start vertex and scene, which actually is in the set, which is a set. We'll say while stack has an element, they're going to pop an element off the top of the stack. Now we want to check if we reach a target node, if node equals end, turn true. Node and scene continue. Otherwise, we do scene.add node and add all neighbors to the stack. I forgot to mention our time complexity for the other one is also going to be our time. Well, the find function runs in constant time average, and we did a linear operation to load in all the edges. That's linear time, but it really depends on how many edges there are. Now, I would say our runtime actually would be the same as this, would be v plus e, right? Because to create the constructor, to use a constructor in the union find class, we have to do v operations, and there's e operations to load the union, the edges into the union, into the quick union data structure, into the union find data structure. Space complexity, ours, right? So we need a root array of v elements. And I actually think ours actually might have less because we have v, right? I think ours actually be O of v. So let's run through how this would work. They have a stack, right? So let's take a implementation here, right, into their version of the solution. I guess we can just do it like this. We could just take a picture of it. and we'll just leave this open, and then we'll just go to the solutions tab. So they create the adjacency list. They create an adjacency list by iterating through the edges and creating a bidirectional edge between A and B in the edge. We start the stack with 1, our source or our start vertice, right? And we say scene is equal to a new set. While the stack isn't empty, right? And the stack isn't empty because there's 0 in it. We're gonna do node equals stack.pop. So we're gonna take 1 off the top of the stack. 0 does not equal 2, right? We haven't seen it before, so we're gonna add 0 to scene, right? Then for every neighbor, we're gonna push them onto the stack. So now we're gonna push 1 and 2 onto the stack. The stack isn't empty. Oh, no. We'll push 1 and 2 onto the stack, so we're gonna pull 2 off of the stack, right? And they actually would return true here. So it actually does make sense for this one. Let's say our goal is 1, right? We'd say if node equals n, it doesn't. If node isn't seen, it's not. So we do scene.add 1. So we'd add 1 to the scene set, right? Then for the neighbors in, I see it. For the neighbors in the adjacency list, right? For 1, we're gonna push on 0 and 2. I see, that was our mistake. I think in ours, if we had seen it before, I think we were returning something, or maybe we weren't, but we probably just wanted to continue. We wanted to ignore it. So then they end up pushing on 0 and 2 onto the stack, and then we get to 2, right? But we're looking for 1, so we found it already. So that is a good version. That's a good version. This iterative version also lets you keep track of the path so far, which is pretty cool. If you reach it, you can just push the path right in this if statement right here. So that's useful. I have to keep that in mind in the future. So we found the path existing graph, and now we have another depth first search on the Explore card. All paths from source to target. So we have all paths from source to target. Given a directed acyclic graph, a DAG for short, so it's directed, which means we can't go from 0 to 1. We can go from 0 to 1, we can't automatically go from 1 to 0, right? It's acyclic, which means I think lacking it's lacking cycles because it's directed. Of n nodes labeled from 0 to n minus 1, find all possible paths from node 0 to node n minus 1 and return them in any order. So now we literally want to find all paths. The graph is given as follows. Graph sub I is a list of all nodes you can visit from node I. There's a directed edge from node I to node graph sub I sub j. So we're given a matrix of edges where each array is a vertice. So the first 0th index has edges 1 to 2, which makes sense. And then we have 3 here. Our vertice 1 has an edge to 3. Vertice 2 has an edge to 3, and our 4th vertice has no edges to anywhere. And here we see that there really are no cycles. We want to know every possible path. So the path from 0 to 4, 0 to 3. But they want to know every find all possible paths. Oh, they want to find all possible paths from 0 to n minus 1. So that'd be 0, 1, 3, 4. So I think what we could do, we can't use union find this time. But what we could do is what they did in the last problem, which I don't know if is cheating since I remember it since we just read it. But we said before that we could generate we could keep track of the paths with a depth first search done iteratively. If we find the node we're looking for, then we'll know that the current path is a possible path to get to that node. But our subpaths count, so we want to find a way to get from 0 to 4. 0, 4 is a path, 0, 3, 4 is a path, 0, 1, 3, 4 is a path, 0, 1, 2, 3, 4 is a path, and 0, 1, 0, 1, 4 is indeed a path. So I'm thinking, what if we did an iterative depth first search? And as we're going through, right, we push 0 onto the stack, right? Then push all our neighbors, which would be 1, 3, and 4, right? We push all our neighbors, right? And if the node equals n minus 1, which it would, so the other thing we need is we actually technically already have an adjacency list, because if we subscript the array, right, we get the array of neighbors. So we technically already have an adjacency list. So if we visit our neighbors, we'll also need to, it seems like we could also keep track of current path, right? And as we go deeper, add to it. As we pop, right, remove from it. So maybe that could make sense. That way we could find all the paths. So the way they set up the stack before, they had the const stack equals our root, which is going to be the starting point. So we want to find all paths from 0 to n minus 1, right? And we're going to say while the stack dot length is not equal 0, right? We're also going to want current path, right, which is going to equal to an array, and we'll also want const all paths, which is what we're actually going to return. And so let current path is going to be actually, since we're starting in the stack with 0, it's probably safe to say that our current path actually does start with 0. But actually our stack will actually handle that. So what we'll say is, we're in here, right? We want to say const cur equals stack.pop. So pop what's off the stack. So we're gonna have 1, right? Maybe we're also gonna need scene so we don't keep visiting. So we'll have a set, which will be a new set of type number, and we're not gonna want to visit what we've seen before. So okay, const cur equals stack.pop. Right now, if cur equals, and we'll say const target is equal to graph.length minus 1, right? Because there's 1, 2, 3, 4, 5 elements, and the goal element is actually 4. So if cur equals target, right, then we'll do current path dot push target, and then all paths dot push current path. So we'll have pushed current path on it, and since it's going to be by reference, we'll just copy it. So we're going to push all paths on. Let's start with the simpler example first. So we have 0, right? We have cur equals target, right? Does 0 equal 3? It does not, right? So now we want to say, hey, have we seen this before? So we'll say set.has cur, right? We just want to continue. We don't want to handle it. We don't want to do anything with it. Otherwise, we haven't seen it before, so let's add cur, right? And this is actually fine because we're going to visit our neighbors now. So we visit our neighbors, and I think one way to do this is actually we'll just say graph sub cur, or we'll just do for const n of graph sub cur, which should be our sort of like an adjacency list. So we're gonna have access to 1 and 2. I'm just gonna say stack dot push n. So we're gonna push 1 and 2 onto the stack. Right, but we're actually not building our path yet still. So I actually don't think we have to push target on here. We can just say current path dot push cur, and cur equals target, then we want to push what our current path has. And then if set has cur, we want to continue, so we're also going to want to remove from our current path. And so let's run in our head this kind of dry run. We'll have 0 in the stack, we pull off 0, we push 0 onto the current path. 0 does not equal 3, right? And we haven't seen it before, right? So we'll add 0 to our set, and then we're going to say const n of graph sub cur. So we have 1 and 2, we're going to push 1 and 2 onto the stack. So then we're going to take 2 off the top of the stack now, right? And we're going to say current path dot push cur. So the current path we have right now is 0 to 2. So we're going to push that on. We're going to say, does cur equal 3? It does not. If set has cur, it doesn't. So we're going to add it, and then we're going to visit the neighbors of 2. So we're going to subscript 0, 1, 2, right? And push 3 onto the stack, right? Then we're going to push, since we have 3 on the stack, we're going to pull it off. We're going to push our path, so we're going to have 0, 2, 3. If cur equals target, which it does, all paths dot push current path, so we're going to push 0, 1, 2, 3 onto the array, which is perfect. And then we're going to say if set dot has cur, right? And it doesn't. We're going to add 3. This could be a problem because we want other nodes to visit 3. But we'll add 3, and then we're going to push. So this is the thing. If cur equals target, we're going to do all paths dot push. So if that's the case, we want to push it. You want to push it, which because we'll have 3, which is a good thing, but then we actually want to backtrack. So maybe after we push it, we could remove the node we just added and do a continue, but then we'd have 1. And so that actually doesn't make sense. I want to say if set has cur, we should have kept track of the stack for this example. So the stack is going to start with 0 in it, right? We pull off 0, we have current path push, we push cur onto the path. Push cur onto the path, which is going to be 0. 0 does not equal 3, right? Does set have cur? It does not. Since set does not have cur, we're going to add cur. So we've seen 0 already. Now we're going to visit our neighbors. We're going to push 1 and 2 onto the stack. Now we're going to pull off the last element on the stack, which is so we're going to push 1 and 2. We're going to pull off the last element in the stack, which is 2, right? So now we have 2 in hand. We're going to push 2 onto our current path. It's not equal to 3. We haven't seen it before, so add it to the set. So we have 0 and 2 in the set. Then we're going to add the neighbors of 2 onto the stack. We're going to push 3 on. Now we have 3 on the stack. right? And we have no more paths for 2, so our current path, right? And then we're going to pull off 3 off the stack. Current path is going to equal, we're going to push 3. 3 does equal target. So we're going to push this array 0, 1, 3, which is good. Set doesn't have 3, so we're going to add. We now have 0, 2, and 3 in the set. Visit any neighbors of 3. Right, we push 3 back onto the stack, but the cur stack, right, cur equals stack dot pop, current path dot push. Push another 3 onto the path, and cur does equal target. So I'm thinking we actually want something different. We push this up here. Now if set has cur, we want to continue. So 3 already exists in the set. So we're going to continue, right? And then we can pull 3 off of the stack. And then we can pull 1 off the stack and visit, right? 1 is not in the set. So I think the problem being if we do set, if we've already seen it, then I think we want to do stack dot pop, but not keep the element. Oh, not stack dot pop, I mean current path dot pop. If we do current path dot pop, that way, right, we'll go 0, 2 to 3, and 3 will be a neighbor itself. We'll push 3 on, pop that off, right? We still have an issue. I kind of want to pop. I think I see what's happening. We don't have to do current path dot pop, but I think what we do have to do, right? I have a step here to back up path till equals cur, right? If set has cur, we continue. We'll get to 1, right? But our path still has 3 and 2 in it. So what we want to do is we want to say while current path dot length does not equal 0, not equal cur minus 1. So we'll say our current path does not equal 0, and current path sub current path dot length basically we want the last element in it before we add our newest element, right, to equal so we're at 0, 2, 3. We want to pop elements off the current path. 3, 2. I guess we could have pushed the previous node as well on, but stack still has 0 in it. So we want to go back basically until we'd like to backtrack current path basically. We want to backtrack current path, so 3, 2. So we're all over the place. Let's restart. We have 0, right? We push 0 onto the stack. Target is equal to 3. Our stack isn't empty, so we pull 0 off the stack. Then we add it to our set, and our set hasn't seen 0 before, right? Then we want to, we'll have current path, or we want to back up, right? We want to back up, right? While current path, which equals 0, while current paths of the last element, which is 0, does not equal what? So we'd actually be fine here. Actually, I think we can do while current path of current path dot length minus 1 does not equal cur, because it should already be we basically said the current stack the current path would be 0, right, 1, 2, and then we'd visit 2, get to 3, right? We basically, once our stack gets back down to, I think our stack is almost a mirror image of the current path. So you'd say 0, 1, 2. I think our stack is a mirror path. I think our stack actually shows our path through. So in cur equals target, all we have to do is push the stack. We would have 0, 1, 2, 3. If that's the case, we actually don't have to do anything with current path, I think. You don't have to do current path dot push either. So we'd say if cur equals target, we want to do all paths, right, dot push, what's currently in the stack along with cur. And then I think we'd have what we're looking for. Then we'd add cur to scene. And so if we do it this way, we have 0, right, in the stack. We pull it off the stack, right? We haven't seen it before. It's not equal to 3, right? So we add 0 to the set. We iterate over its neighbors. We have 1 and 2. We push 1 and 2 onto the stack, right? Then we pull 2 off of the stack. So now we're holding to okay, so the current path, we were on the stack does not indicate the current path. Current stack does not indicate the current path, so we could say we'll bring back our current path idea. We pop something off the stack, we'll do current path. We haven't seen it, we'll do current path dot push cur. We want to push here is a copy of current path. Now the final key to this problem is just how to keep current path updated with our current path. So I have 0, right, 1, right, we have 0, we push 0 as a current path. We have it's not equal to 3. It's not in the set. We add it to the set. We iterate over our neighbors. We push 1 and 2. Then we pull 2 off of the stack. We haven't seen 2 before. We push it onto our current path, which is actually a path 0, 2. It's not equal to 3. So we add 2 to our scene set. Iterate over the neighbors of 2, it's only 3, so we push 3 onto the stack. We pull 3 off the top of the stack. We haven't seen 3 before. We push our current path, which is 0, 2, 3. Cur does equal target. So we want to do all paths dot push current path. Now we've seen 3. Now we've seen 3. Right now we've seen 3, and we're going to iterate over the neighbors of 3. It has none. So the next element we take off the stack is going to be 1. But the current path looks like this, 0, 2, 3. But the next element, next time we actually work with the stack, this is what it looks like. So I think what we want to do is say, if all path dot push current path, right, we want to remove nodes from current path until cur path minus 2. Oh, no, cur path, right, sub end, the last element in cur path, right, is equal until cur path sub end, right, so we pop 3 off, 2 off, right, until it's equal to stack sub length, right, which is 2 minus 2. So I think we can do that. We'll say while stack, when current path, we'll say while current path dot length does not equal 0. Or while current path dot length is greater than or equal to 2. Well, we want to remove nodes from it, so it just needs to have 1 node. All right, so while it doesn't equal 0, right, and current path sub current path dot length minus 1, so the last element in it, right, does not equal stack sub stack dot length minus 2. Right, what we want to do is do current path dot pop it at the end. We also want to make sure, right, that and stack dot length is greater than or equal to 2, so that we don't do any out of bounds. We'll make this slightly smaller so it's readable. It's still unreadable, and we can break the cases up. So I think this does make sense. So then we go all the way, we bring current path all the way back down to 0. Then we take 1 off the stack. Have we seen 1 before? We haven't. We push 1, right? 1 does not equal 3. So we add 1, visit 1's neighbors. 1's neighbors, right, are 3, right? And we'll make a special exception. Make a special exception, right, if set has cur, right, and cur does not equal target, right, then we'll continue. Otherwise, we still want to visit it as a valid node. And so I actually think this could work. So we have 0, 2, 3. Then we have 0, 2, 3, 1, 3. So our 2, 3 path is still in here somehow. We get the last element. So why is this happening? We have a 2, 3 here. This is unreadable like this. So we have while current path.length does not equal 0. So somehow we're having these two values in between. If we get the last element and it's not equal to stack.length, so we have stack.length. So let's run this. We'd have 0, right? Stack isn't empty. Cur equals stack. So we haven't seen 0. Does the set have 0? No. Right, let me push 0 onto the current path. 0 does not equal 3. So we add 0 to the set. We add 0 to the set. Then we visit its neighbors, which is 1 and 2. So we have 1 and 2. Now on the stack, we pull off 2, right? We haven't seen 2 before. So we push 2 onto a current path. So 0, 2, we add 2, right? It's not equal to 3. We visit 2's neighbors, which is actually 3. Right, so we push 3 onto the stack now. So what's on the stack is actually 0, 1, 3. And we haven't seen 3. So this doesn't work. So we push our current path, which is cur, which is 3. We add 3 to the seen set. If cur equals target, so 3 does equal target. So we do all paths.push current path, which is 0, 2, 3. Current path isn't empty, right? And stack.length is greater than or equal to 2. Stack length has 3 elements in it. I'm going to say current path of the last element, which is 3, while 3 does not equal stack sub stack.length minus 2 is strange because our stack is 0, 2, 3 and our actual stack is 0, 1, 3. And our actual stack at the time is actually 0. Our actual stack at the time is actually 0. Our actual stack at the time is actually 0, 1, 2, and then we visited 3. So our actual stack is 0, 1, 2, 3. Oh God. Let's print current path and stack. So we have 0, 2, and 1, which is currently in the stack, right? Because 0 is not in the stack anymore. All right, that is interesting. So 0 is never really in the stack. We'd like to pop it back all the way down to 0, but it actually doesn't make sense. 0, 2, 3, 1. So our approach is what we think is happening is just not happening. What we think is happening is not happening. It's 0, 2, 3, 1, 0, 2, 3, 1, 3. we could keep track of, no, that doesn't make sense. It will be pushed on tuples, so we could say where we came from. That's the case. In our stack, we'd have a tuple of 0 to 1. This iterative version is strange. I think we could do a version that generates all paths. That version would be done with recursion, and what is different there, we visit all nodes, we push them on. If it's a valid, we never had to keep track of the path though, we only had to actually visit all valid paths. What if we kept a parallel stack of path? So we start at 0, we'll actually say that our path is current path sub 0. Right, we'll pull 0 off the stack, which means we pull current path off the stack. Which means we'll pull current path off the stack. We'll visit the neighbors, we'll push the neighbors on, but they'll also have their own matching paths. So when we push the neighbors on, it'll actually be the concatenation of the current path and the new nodes. So I have 0, 1, 0, and 0, 2. That way, if the node ever equals 3, you can just push the current path. Then we could get rid of all of this stuff here. We push current path. And then instead of current paths, we'll call it all paths or path stack. Then current path will just be the path stack dot pop as well. So we'll pull 0 off, right? Our path stack is going to start with 0 as our start path as well. We'll have the stack path stack and all paths, which is our goal, which we want to return. So with 0 in the stack and 0 in our path stack, we'll pull off 0, pull the current path off, and we'll say, hey, does set have cur? It doesn't, so we can do nothing with the current path. Because we already have it, so you want to add 0. Cur does not equal 3. We want to visit our neighbors. When we push them onto the stack, we actually want to do path stack dot push, right? Whatever is in current path, right? And n. That would actually just be 0 and 1 and 2. So then we go to 2, right? And we pull its stack off the top, right? We have the path stack. We get that path. It's just 0, 2, right? Have we seen 2 before? We haven't, so we add it. 2 does not equal target. So we visit the neighbors, and there's just 3. So we push 3 on, but it's actually going to be 0, 2, and 3. And then we're going to say cur equals stack.pop in the current path. If set has 3, which it doesn't, we're going to do set.add cur, right? And if cur equals target, which it does, we'll actually just push, right, a copy of the current path array, and then we'll actually just do set.delete cur so we can revisit it. And I actually think this makes the most sense so far. Where's the sidebar? How do you know if you solved it? Oh, we failed. We ended up creating 0, 1, 2, 3, 4, 0, 4. So we 0, 1, 2, 3, 4 is valid path, 0, 1, 4 is valid path, 0, 4, and we're missing 0, 3, 4. So it's close. I think this is actually, so we're missing 0, 3, 4. Now I wonder why that is. If we start at 0 and we push our neighbors, we have 3 and 4. In the path stack, that would look like 0, 3 and 0, 4. 0, 4, which is actually a valid one. Oh, 1, 3, and 4. It's actually 4, 3, 1. So 0, 4 is the first one that gets added. And then in our submission, oh no, we actually have to do 0, 1, 4 first. So 0, 1, 4 is actually not a valid path. Wait, it is? I think we're confusing this. This is not the same. 4, 3, 1, 3, 2, 4, 3, 4, empty. Right, this is the same graph. So how is 0, 1, 4 valid? Oh, 0, 1, 4. Right, so we do get that as a valid path. The next one we return is 0, 1, 2, 3, 4. Right, so we end up visiting 3, which means actually means we can't revisit 3, which is actually not good. I don't know if we have to add every node we visit. I think after we finish visiting all the neighbors for a node, then we can add it. I think that original example no longer, so we actually get 0, 2, 3. Right, so it's a case where we have the scene, but if we want to visit every path, we actually end up being unable to visit every path because our scene set prevents us from doing that. It's actually a problem we have with a lot of graph problems, actually. We're finding one way through that seems to help us, but we have to find multiple paths, and the scene set gets in the way. Maybe it's not when we start that we'd like to quit, but more so when we're visiting neighbors. If we change where we check, so when we visit neighbors, we're still allowed to do what we want to do. And then we can do set.add n. So we still fail here. We only generate one after visiting all of its neighbors. Set that. So now we're just kind of guessing, which is not good. Our set array is getting in the way of us checking all valid paths. Maybe as we pop values off the stack, we also want to delete them. So we'll say set.delete cur if it exists. Yeah, we're just guessing at this point. We visit it. I think this would be much easier with depth first search and backtracking. So if we do the same thing, except we'll do a DFS, we'll do DFS graph, right? Vertex, which we want to start at, right? And all paths, which we want to add to. And I think we can just still return all paths. We'll have this DFS function. Which would take the graph, right? The vertex, which would be a number, and then all paths, which would be an array of numbers, right? Which we're going to modify by reference. And then the call stack will do the backtracking for us. Do we still need the visited set? I think we still might need the visited set. If we use the visited set with recursion, the paradigm is still the same. If it exists, then we wouldn't be able to generate all pairs. It's acyclic, so we actually don't have to worry about cycles. I just realized that. The graph is acyclic, so we don't have to worry about cycles. I think we actually don't need the set at all. Ugh. Reading the problem is too important. Oh man, yeah, like I just remember they said there's no self loops and the graph is acyclic, so we don't have to worry about cycles. We don't have to worry about cycles, and we don't need a set. Oh, that's too important. I think that's why I struggle with such a good elaborative encoder. There's no cycle, so we don't actually have to use the visited set. We just want to visit all of the nodes, and so there's no cycle. We know we won't run into previous ones. We won't loop forever. That is very interesting. The time complexity here would just be, I think it was still good though that we came up with the path stack. That was a really good idea that actually worked really well to iteratively generate the paths. We just didn't need the set. It was reducing our total number of elements that we could generate. And I think we'll do linear time to visit. Actually, it's going to be O of V times E. We're visiting every vertice. We're going to visit every edge that every vertice has, generate all the paths. And we're using a stack and a path stack. And at worst, this could have n elements within it. So it'd be linear time or linear space, well, I want to say v times e's time. Is ever given on the problem description, I'll be backtracking. Path exploration in a graph data structure is the perfect scenario to apply the backtracking algorithm. As a reminder, backtracking is a general algorithm that incrementally builds candidates to the solutions and abandons a candidate. Backtrack as, wow, interesting. This is actually backtracking with the path stack. Determines the candidate cannot possibly lead to a valid solution. For more details about how to implement a backtracking algorithm, one can refer to our Explore card. Specifically for this problem, we could assume ourselves as an agent in a game. We can explore the graph one step at a time. Any given node, we try out each neighbor node recursively until we reach the target, or there is no more node to hop on. By trying out, we mark the choice before moving on, and later on we reverse the choice, backtrack, and start another exploration. To better demonstrate the idea, we illustrate how an agent would explore the graph with the backtracking algorithm. Following image where we mark the order that each edge is visited. 1, 2, 3, 4, 5. The idea might remind one of the depth first search traversal algorithm. Indeed, often the backtracking algorithm assumes the form of DFS with the additional step of backtracking. And for the DFS traversal, we often adopt the recursion as its main form of implementation. The recursion, we could implement a backtracking algorithm in a rather intuitive and concise way. We break it down to the following steps. Essentially, we want to implement a recursive function called backtrack cur node path, which continues the exploration given the current node in the path traversed so far. Then the recursive function, we first define its base case, when we should terminate the recursion. Obviously, we should stop the exploration when we encounter our target node. Condition of the base case is cur node equals target. The body of our recursive function, we should enumerate through all the neighbor nodes of the current node. That's basically what we're doing here. For each iteration, we first mark the choice by appending the neighbor node to the path. Then we recursively invoke our backtrack function to explore deeper. At the end of the iteration, we should reverse the choice by popping out the neighbor node from the path so that we could start all over for the next neighbor node. Once we define our backtrack function, it suffices to add the initial node to kick off our backtracking exploration. So our target is the length of the graph minus 1. Result is this array. Backtrack is cur node and path. If we reach a target, no need to explore. Results.append list path. For next node in graph, we do path.append next node, backtrack, next node path, and then we pop the next node. So here we just kick off the backtracking, starting from the first node, path deck, so 0, backtrack 0, path. Interesting. Yeah, I think I'm realizing now we've written a lot of backtracking algorithms, just didn't realize we were backtracking. Let n be the number of nodes in the graph. First of all, let's estimate how many paths there are at maximum travel from node 0 to the node n-1 for a graph with n nodes. First of all, let's estimate how many paths there are at maximum travel from the node 0 to the node -1 for a graph with n nodes. Let's start from a graph with only 2 nodes. As one can imagine, there's only one single path to connect the only 2 nodes in the graph. New path, old path. Now let's add a new node into the previous 2 node graph. We now have 2 paths, one from the previous path and one is bridged by the newly added node. If we continue to add nodes to the graph, one insight is that every time we add a new node into the graph, number of paths would double. With the newly added node, new paths could be created by preceding all previous paths with the newly added node. As a result, for a graph with n nodes, at maximum there could be summation of I equals 0 to n-1, n-2, 2 to the I equals 2 to the n-1, minus 1. Time complex would be 2 to the n times n. So we calculated shortly before there could be at most 2 to the n-1 minus 1 possible paths in the graph. For each path, there could be at most n-2 intermediate nodes. It takes O of n time to build a path. To sum up, a loose upper bound of the time complexity of the algorithm would be 2 to the n-1 minus 1 times O of n, 2 to the n times n. Consider it takes O of n efforts to build each path. It is a loose upper bound since we could have overlapping 2n times n. Interesting. Interesting. Backtracking. Interesting. Backtracking. Interesting. Backtracking. Backtracking is definitely going to be an explore card we have to revisit. And let's see if I can find that other problem. Explore card. All paths from source to target. And it auto pastes. Seems to auto paste our code to solve it in the actual window. And then we have clone graph. We actually have that loaded up right here. So 16 minutes. Given a reference of a node in a connected, if it's connected and undirected, what does connected mean? Does that mean fully connected? Or a deep copy or clone of the graph. So this connected means it's the minimum number of edges required to be able to reach any node from any node. Each node in the graph contains a value int and a list node of all its neighbors. So basically, you have to clone this graph. We have to clone this graph. We have to clone it. So I think we could clone it a depth first search. I think we could clone it with a depth first search. Clone with DFS recursively, and the goal would be to have a map of values to nodes, but this would assume that the nodes are unique. The values of the nodes are unique, and let's check if that's true. Node.value is unique for each node, which means you can use it as an ID. There's also no repeated edges and no self loops, which doesn't mean that there's no loops at all. It doesn't say that the graph is acyclic, so it means that the graph could contain a cycle. The graph is connected. All nodes can be visited starting from the given node. And the graph can be empty, so we'll say if not node, then we're going to return null. Now if we want to clone, map with DFS recursively, we're going to need we're going to need a couple of things. We actually don't need to have an adjacency list of this node, since node itself kind of helps us with that, since we're going to be trying to visit every node. But we could have our own, which we could call const clone, which would be a new map of type number to node. And the goal would be, as we're visiting these nodes, right, we're going to start from a particular node, right? And if the node doesn't exist, node doesn't exist, then create it. Right? Node doesn't exist, then create it. If that's the case, right, we're going to create it so we could visit 1, right, doesn't exist, right, and so we're going to have to make sure we use a visited set or scene set, because the graph can be cyclic, so we're going to need a scene set. We're going to add 1, and if it doesn't, node doesn't exist in clone, node 1 won't exist in clone, so we'll create it with a node val, so it will be cloned, then we'll create it. Then we're going to visit our neighbors. So we're going to say, hey, does 2 exist? 2 does not exist, so create it. Then we can create it and add it to create it, right? Create and add children, right? And then we want to visit those children as well. So we'd visit. So if we created 1, right, we create 2, add as a child of 1, and then visit 2's children, which would be 3. 3 doesn't exist, so we create it, add it to the set, and visit its children, which would be 4. But now this is actually a problem, since we'll have visited 4, and if we go back to 3 to 1, and to 1 we try to visit 4, we'll already have seen 4. So maybe what we can do is actually only check the set on neighbors. So we can visit 1, right, visit 2, and if 2 exists, 2 doesn't exist, we'll create it, then add it. So it's similar to our problem before, right? In the previous problem, we forgot to remember that the graph was acyclic and directed, so we could just visit all the nodes without worrying about anything. In this one, there could be a cycle, and we can see that there's a cycle, so you have to worry about revisiting. So we could do the thing where we filter out simple cycles. We go to 1, then go to 2, filter out the simple cycles. We don't want to go back to 1, but it's bigger than that because we can't even go from 1 to 4. It might actually just be easier to clone if we just created an array of edges. So what if we just created an array of edges? We would just visit, right? We'd say, hey, edge between 1 and 2, right? We'd visit it as an edge between 1 and 2. We'd add it to our edges, right? And then we'd add an edge between 1 and 4, right? And 4 and 1. We'd add an edge between 2 and 1, right? And then we'd visit 2, add an edge between its neighbors, 1 and 2 and 2 and 1. And then, so yeah, I think we could do that actually. If we had this array of edges, we have 1, 2, 2, 1, 2, 3, 3, 2, 4, 3, 3, 4, 1, 4, 4, 1. We have this array of edges, and we'll just say, hey, if we haven't seen this edge before, create it, right? And also, if this edge doesn't exist in its list, then create that as well. So I actually think if we had the edges, then we could know we could clone it pretty simply without having to traverse the graph, and we could just create a map with the nodes, and then we could just link them to one another. It actually looks like the order does matter here, so I'm wondering if we can return clone any output. Actually, they'd like us to return as a node, so I think we could do this. So we'll say const edges equals an array. We'll say find edges of node, and we'll pass in edges. This is going to be a DFS, so we'll have find edges. I'm going to take a node, which can be node. It can't be null since we're only visiting nodes we know. And we're also going to have a set, right, of numbers. This one we don't have to worry about making those mistakes. We'll have edges, which will be an array of numbers, an array of numbers, and then we'll have a scene, which will be a set of type number. We're not going to return anything. I'm going to say if scene has not seen node.val before. So if we haven't seen it before, first thing we're going to do is add it, right? And then we're going to iterate over the neighbors. We're going to say for const n of node dot neighbors, and we're going to first do edges dot push node dot val to n dot val, and then we're going to do find edges of n, edges and scene. I think if we do console.log edges, we should be able to hopefully see this array of edges we've created, and we'll just return null for now to see if this makes sense. Oof. Right, node. We want to push an array of numbers, so node.val to n.val and n edge scene. So you have 1, 2, 2, 1, 2, 3, 2, 3, 3, 2, 3, 4, 4, 3, 4, 1, 1, 4. So this actually works perfectly. Visit the node, right? If we haven't seen before, we visit its children, we push it, then we find the edges. And now to clone it, we could do for const v1 of v2 of edges. We'll say call it clone map. It'll be a new map of number to node values, and we'll say if clone map, right, clone map, wait, what? If clone map does not have v1, then we want to create it with that value, right? And we can actually do this for v1 and v2. We'll just do dot for each. We'll do clone map dot set v to new node, right, with v as the value, and then we can print clone map So we should just have the nodes with the empty neighbors. So this actually works perfectly. And then we can do one more iteration. We basically want to add an edge. Yeah, we need to revisit this one. I'm sure we could get to a solution, but the solution feels more like working through programming issues than actually having an angle that makes sense. So our depth, so we're doing a lot of like, we find the edges and then we create a clone map. And while I'm sure this could get us to a solution eventually, because we could just keep doing operations based on the structures we're creating, but it doesn't really feel like there's an angle here that uses any of the knowledge we currently have. We can do a depth first search, and I'm sure we can clone it as we're traversing through it. We have the node. If we haven't seen the node before, then we'll create it, and then we could add the node as a neighbor. If we're visiting it, it doesn't make sense. Because we're able to visit, it now. So I'm thinking we could just pass in the clone map. A map of number to node, right? If we haven't seen this value before, it means it doesn't exist in the clone map. So do clone map dot set node dot val equal to new node of node dot val. We can also do const created, right? And we'll set it equal to what we just created. So it's like clone map dot set node dot val created. We're iterating over our neighbors, right? And we have const n of neighbors. Instead of pushing the edge, you can say if clone map, right, clone map does not, and so we're actually bridging a gap here. Scene is supposed to be helping us for visited, but clone map is also helping us for visited. So in clone map, right, does not have n, right, then we're just going to do the same thing we did any up there. We'll create a constant new node, right, with n dot val, and this is n dot val as well. And we want to do created, right, dot neighbors dot push, and which we just created, and then we'll do find edges. It's no longer really find edges, but then we'll in clone map to see what we actually get. We'll call this nay. Four has no neighbor, so visited does end up getting us in the end. Maybe we still want to visit it, right? We're being too, aggressive with the visited array. So this is actually us only using seen. We visit all of them anyway. This can't possibly work. So let's return clone map dot get dot val. I'm sure to work for this first example. There's no way it passes all the. Those are a copy of all the nodes in the original graph. Okay, new n dot val, and then we push nay. Clone map dot get. They're saying we're not. Let's run a copy of all the nodes in the original graph. So is this not a copy? Constant. Okay, a new node of the neighbor, right? With n dot val, we do created dot neighbors dot push nay. And we find next edges of the node that actually does exist. If we haven't seen this value, then we create a new one of the value to created. This should be a brand new one. This shouldn't actually be a, it should actually be a copy. Seeing, right, the node's value, create a new node with the value set, clone map to that created value. We visit the neighbors, we create a new node. The neighbors that we push on are actually nay. Yeah, I'll have to come back to this one tomorrow.